I'm Brian Grisey with Edge Technologies. This is part 2 in a series related to bar feed remnant length in Swiss machining applications. In part 1, I talked about how a remnant length is determined in a machining application, and I focused very briefly on some of the variables that cause a remnant to be the length that it is. And if you haven't watched part 1, I recommend that you go back and watch part 1. I feel it's very informative on the basics of how the remnant length is determined. In part 2, I'm going to focus a little more specifically on one particular variable that causes the remnant length to sometimes be excessive, and focus in a little more detail so that we can accurately set this particular setting in the process. The setting that I'm talking about is the regrip length, and I talked a little in part 1 about the minimum possible remnant and how we get to that, being the distance from the cutoff tool to the back of the bar inside the bar feed collet, through the guide bushing, through the main spindle collet. And I talked about a position of Z-axis forward soft limit or over travel position, that being the position of the main spindle headstock when the machine is at the machining point of cutoff. And this headstock being in this forward soft limit or very, very close to it is very important in minimizing the remnant length. So how do we get that there? Because when we're machining a Swiss application or sliding headstock application, obviously this Z-axis is traveling forward and back as we're machining. And at the end of the machining process, when we're parting off, we want to have, like I say, we want to have this headstock at the forward position. And there's a way to set that up to get it there, and that varies a little bit from machine to machine. And it's very important that we get it there, because any distance that's left between this soft limit position and where the headstock is at the point of cutoff is going to be waste material. And obviously we want to eliminate that. We want maximized efficiency here and minimized waste. So we want to minimize this gap here. And this gap, if not set correctly, obviously we're gonna leave quite a bit of material based on how much distance we leave between these 2 points. Okay, so how we get there, we're going to call regrip length in most scenarios. And the regrip length is a very simple mathematical equation of your finished part length plus the width of your cutoff tool, and that's the blade, plus a facing width, which is typically, 50 thousandths roughly, how much you're facing at the front of the bar to clean up the part prior to starting your machining process. Plus a small safety length so that we don't actually run into the over travel or the soft limit and alarm the machine out. Generally another 50 thousandths or so roughly. That added together is the regrip length that we're going to use. So if we add some numbers into that, we add our finished part length of roughly, let's call it 3 inches in this situation. Let's say our cutoff tool width is 92 thousandths. Our facing width, like I said, is maybe 50 thousandths, and another 50 thousandths safety. That leaves us with a regrip length of 3 inch, 192 thousandths. Okay, that would be a typical scenario for a 3 inch finished part length. Obviously, you're going to vary from this a little bit based on what your particular setup is, but that's just a rough estimate based on some assumed values here. Another thing that's very important that I'm going to mention here is the bar feeder part length parameter. So I talked a little bit in this the first video about the part length parameter in the bar feeder, and in this scenario here I want to point out that the part length parameter is not set based on the finished part length. It's set based on the regrip length in order to not only maximize the usage of the material, but also to guarantee that the bar feeder has the accurate value to make a bar change at the right time and not wait too long and not run into a situation where it actually crashes. Because of these additional values here, this additional 192 thousandths in a 3-inch scenario, not generally going to cause an issue. But let's say you're machining a very, very small part. Let's say you're machining, some washers or something like that, something very thin. Let's say your part thickness or your part length is 100 thousandths. You add another 192 thousandths to that, and that's a significant difference in your regrip length versus your finished part length. And the bar feeder needs to know that in order to accurately determine when to make a bar change. Okay, so this is what makes up the regrip length. And again, if that length is not entered correctly into the lathe, you wind up with waste right here. So your regrip length, being the 3-inch 192 thousandths that we just determined, would put your sliding headstock here at the point of cutoff. If the value that you enter into your program or into your lathe setup puts the headstock back here, this is wasted material. And in this scenario, it looks like about 1 full part length. So you've wasted a part. So you've wound up with one entire part that you could have machined had the equipment been set up properly. That one part winds up on your remnant and in the scrap bin instead of in the parts bin. Okay, and that's a pretty significant loss of value there. So that's what we're going to try and minimize. So how do I set this up? Right? That's the next question. How do I set this up so that this regrip length is in my machine properly so that I eliminate this excess right here? Okay, and that's going to vary by machine make and model. Okay, your lathe make and model is going to determine how you set that up, and I'm going to request that most effectively refer to your lathe operator manual how to set that. But I have a couple of examples here that I'll provide you with some of the most common lathe make and models, or the makes anyway, with the method that they use to set this distance. So how do we set this distance when we're referencing a Tsugami or a Hanwha Swiss lathe? The regrip length is going to be found in your G300 line of code. Okay, so at the beginning of your lathe program, typically at the beginning of the program, you'll have a collet open with a regrip sequence, and in that sequence you'll have a line of code that starts with G300, and that G300 is the instruction to the lathe to find this position, and in this case we enter in whatever the regrip length is that we calculated, 3.192 inches. Okay, or obviously if it's metric, you're going to calculate in metric, and it's going to be a negative value. So what you're doing is you're subtracting from this soft limit position. You're telling it from here we want to go in the negative direction, 3.192 inches, and that's our regrip position, and that's going to give us the most accurate positioning so that we can minimize our remnant length and not have that waste. On a Nomura, very similar process. We're going to find our regrip length the same way, and we're using a G62 instead of a G300. The G code will be in the same location after the collet open command near the beginning of the program. You'll have a G62 followed by your Z minus 3.192 in this scenario, or whatever your regrip length has been calculated to be. Okay, so those are 3 examples there. If we move on to a star machine, the star is a little bit different. Similar in that we still have to calculate the regrip length, but different in that the star actually subtracts the regrip from the total Z-stroke of the machine. So whereas the Tsugami, Hanwha, and Nomura is referencing this value from the forward soft limit, the star is referencing it from the rear soft limit. Okay, so if we take the total Z-stroke of the machine, for example, 12 inches, okay, which you'll calculate based on your machine model, the total Z-stroke, subtract the regrip length that we calculated, still 3.192, and we get a Z-stroke position of 8.808. Okay, that's our Z-stroke position, and that's what star uses, the Z-stroke position. And you're going to find that Z-stroke position under your custom menu within your machining data, and you're going to set that up as you set up your part length. Okay, so very similar process, just adds one more step, again because it's referencing off the rear limit rather than the front limit, but we're still positioning its headstock to 3.192 from the front limit. Okay. The next example I have is on a Citizen. On a Citizen machine, we're going to use the regrip length again from the front soft limit, but they set it actually in a machine data page. Okay, they call it machining length setup, and it's found on the machine data page. And I have an example here of what that machine data page looks like. When you set up your part, you'll set up this machine data page, obviously with your bar stock, with your cutoff tool, with your feed and speed here. And here is the machining length, and this is the value that you're going to add right here. So this is where you're going to place your regrip length in the Citizen lathe. Okay, and that's actually a setting in a parameter rather than being data in your program. Okay, so that's a little bit of difference in the Citizen versus the previous makes that I discussed. So obviously setting those is not terribly difficult, but understanding the math to set that value properly is critical for eliminating this waste, and that's what we're trying to do here, right? There's still going to be some scenarios where you have a long remnant due to the part manufacturing process based on your specific part and your specific process. What I'm going to do is I'm going to follow up with a third part to this series where I describe what can we do when we still have a remnant that's unmanageable even after we've maximized all this programming to minimize the remnant as much as possible, and I still have a remnant that's unmanageable. What can I do? There are a few things that you can do in those scenarios, and I'll focus on that in part 3. So hopefully this has been helpful to you, and hope to see you in part 3. Thanks.